Okay, so today we're going to look at section 2.2, which is polynomial functions of higher degree. So we're looking at functions like x cubed, x to the 4th, x to the 5th. Okay? And there's a few characteristics of polynomial functions that we need to know. The first characteristic about polynomial functions or power functions is that they're always continuous. Okay? So you'll never have a break in a polynomial or power function. The second thing we know about them is that they have smooth, rounded terms, not sharp-pointed terms like absolute value graphs. They're very smooth in their curves. And then the last thing that we need to know about them is that the bigger the exponent, the flatter the graph at x equals 0. So an x squared graph isn't very flat at all at x equals 0, but an x to the 4th graph is much flatter when we hit x equals 0. And we'll look at that, look at the different graphs together in a minute. Okay, so let's look at some even functions and some odd power functions and look at their characteristics. Okay, so the first thing that we said that was characteristic about them is that they're continuous. And so if we notice on our graphs are in fact continuous. They keep going on forever and ever and they don't have any breaks. The second thing we said was that they had smooth, rounded curves. And we notice like on our x squared and our x to the 4th that those are smooth curves, those aren't sharp points. And then the third thing we said was that as the bigger the exponent, the flatter they get at x equals 0. So we notice that x squared only is a tiny little point at x equals 0, but x equals 4th is a little flatter. And if we look at the same thing on x cubed just goes through point x equals 0, but x to the 5th sort of stays flat at that point. And it's easier to see if you look at the pictures in your book on page 137. It's harder for me to draw them on the board, but page 137 has good pictures of them as well. Okay, so let's look at actually graphing some of these functions. Okay, so we have f of x equals negative x to the 5th. And we could make a table of values, or we could start with the information that we know about x cubed functions and what those look like. And we know that x to the 5th functions look very similar, with the exception that they are flatter at x equals 0. So we know it's going to be flatter at x equals 0. Whoa. Oh, that's interesting. It's like creepy. Okay, so we know it's going to be flatter at x equals 0. We'll make a table of values just a little bit so that we can sort of guesstimate our point. So we know negative 1, 0, and 1. So if we plug in negative 1 to the 5th power ends up being negative 1, but this is negative, so this ends up being negative 1, which is positive 1. Okay, 0 is 0, and then 1 ends up being negative 1. Because 1 to the 5th is 1, except this was negative. Okay, so then if we plot those points, negative 1, 1 is up here, 1, negative 1 is down here. We knew that it was going to have that similar shape to our x cubed graph, and we also knew it was going to be flat at 0, so I drew it very flat at 0, and then it's steep. So x to the 5th would look, negative x to the 5th would look something like this. Okay, the main characteristic that we needed to note was how flat it was at the 0. If we do the same thing for x plus 1 to the 4th power, we know that even exponents have U-shaped graphs. So we know it's going to look very similar to our parabola. If I draw a couple of points, I get negative 1, 0, and 1. Negative 1 plus 1 is 0, so 0 to the 4th is 0. 0 plus 1 is 1, 1 to the 4th is 1, and 1 plus 1 is 2, and 2 to the 4th is 16. Okay, so if I graph those -1 zeros here, 0, 1 is up here, and 1, 16 would be somewhere way up there. And then I also know that these have to be U-shaped graphs, so I know that it's going to be a U-shaped graph, but it's going to be very flat at the vertex, because it's always the bigger the exponent, the flatter at the vertex. Okay, so that one just looks a lot like an x squared graph, and they will. X to the 4th and x to the 6th will look a lot like an x squared graph. The other thing then that we need to note is what's called our leading coefficient test, because our leading coefficient test tells us what the end behaviors of our graph look like. And I know Mrs. Linseth used to do an end behavior dance. I'm not going to do that. No. Okay, so if your a sub n, that's your leading coefficient, is greater than 0, then your endpoints are going to end up. And that's if it's an even function. Even functions, your endpoints are always the same direction. So if it's an even function and your leading coefficient is positive, meaning it's greater than 0, then your endpoints are up. If your leading coefficient is negative or less than 0, then your endpoints are going to be down. Okay? So that's for any even function. Odd functions are different because the endpoints go in opposite directions. Okay, so an odd function, if your leading coefficient is greater than 0 or positive, then it starts down, and as you go left to right, then it's going to end up. So starts down, ends up. And it's exactly the opposite if it's an odd function and your leading coefficient is less than 0 or negative. It'll start up, and then it's going to end down. Okay, we'll try that again. Okay, so 4 is even, so it's going to be an even function. There is no number out front, which actually means that there's a 1 out front. So that means that my leading coefficient is 1, which is greater than 0, because it's a positive number. So I'm going to apply my even function rules for a leading coefficient greater than 0, which tells me that my graph starts and ends up. So it's going to look something like that. Okay, let's look at one more just for good measure since I didn't record the first one. We look at my exponent. My exponent is odd, so I know this is an odd function. I don't have a leading coefficient, which means that there's a leading coefficient of 1. 1 is greater than 0. So this is going to be an odd function that starts down because it's greater than 0 and ends up. So it looks something like that when it's graphed. Okay, and then the last thing we're going to do on this assignment is find our zeros. So find our zeros of a function f of x equals negative 2x to the 4th plus 2x squared. We actually set our equation equal to 0. So we get 0 equals negative 2x to the 4th plus 2x squared. And we need to solve that for x. So I can see that I have a 2x and a 2x, and I've also got common exponents of 2. So I'm going to factor out a 2x squared from my equation. Okay, and then when I do that, I still am left with negative x squared, because I still have 2 exponents there, and plus 1, because if I were to multiply it back through, I'd need that 1 to hold that place value of the 2x squared. Okay, and this is still all set equal to 0. And so then what that tells me is either 2x squared equals 0 or negative x squared plus 1 equals 0. Okay, well then if I solve this one for x, I divide by 2, so x squared equals 0. Then you take the square root. Square root of 0 is 0, so x equals 0. So I know that my first answer is x equals 0. I know that I'm going to end up with 4 answers because my exponent is 4, so I need to find the other ones. Okay, so then if I go to solve this for x, I subtract 1, subtract 1. So I get negative x squared equals negative 1. Then we divide by negative 1 to get rid of that negative 1. So x squared equals 1. And then take your square root. So x would equal positive 1 and negative 1 when we do our square root. And then we notice that we only have 3 answers though, and remember our exponent was 4, so we have to have 4 answers. That other one comes from the fact that if I take a square root, I'm supposed to get a positive and a negative answer, positive, negative, 0. But that doesn't exist, so 0 is what we call a double root, meaning there's actually 2 solutions at 0, but we're only going to represent it once, because it would be silly to write x equals 0 a second time. So that's where our 4 comes from. There's 2 at 0, and then 1 at positive 1 and 1 at negative 1. Okay, and you can see that pretty easily when you graph 2, because if you graph them, the flatter it is, like if it bounces off of your x-axis, that means it's a double root. Or if it ends up being really flat at one particular spot, it's a double root. So that's how you can tell when you graph. It's either going to be really flat or it's going to bounce off of your x-axis if it's a double root.